Okay, so in this section, we are moving away from trigonometric functions, and now we're going to talk about integrating rational functions. So, a rational function is a ratio of polynomials. So, it's a fraction with a polynomial on the top and on the bottom. And we have a pretty effective strategy for dealing with these things, which is called the method of partial fraction decomposition, where the whole idea is that through some algebraic trickery, we are able to take this ratio of polynomials and split it into smaller pieces, where the smaller pieces can be effectively integrated. Namely, the smaller pieces will be integrated using one of these formulas here, which I have included for reference. Of course, you can prove all of these. This guy you can prove just by doing a U substitution. This is a formula that we've already seen from the section on inverse trig functions. And this guy you could also prove just by doing a U substitution. Okay. So given a rational function n over d, where n and d are both polynomials, recall that the degree of a polynomial is the highest power. So for instance, the degree of this dude is going to be 3, because the highest exponent that appears is 3. So the first strategy that we have for taking rational functions and splitting them into pieces is to notice that if the numerator has a larger degree than the denominator, or equal degree, then we can use polynomial long division. And polynomial long division is going to rewrite the rational function to look like this. So that already splits it into two pieces, where this chunk here, the degree of the numerator is strictly smaller than the degree of the denominator. So, I won't blame you if you haven't done polynomial long division in years. So here is the algorithm for doing polynomial long division. And then I just do an example here. So 1, divide the leading term of the numerator by the leading term of the denominator, and that gives you a term in the quotient. So for example, here we're going to do this integral just by performing long division on this rational function here. So I go through the steps in the algorithm. So 1, divide the leading term of the numerator by the leading term of the denominator. So x cubed over x is equal to x squared, and this is going to give us a term of the quotient. 2, multiply d, the denominator, by the result of step 1. So x minus 1 times the result of step 1, which was x squared, and that gives us this. 3, subtract the result of step 2 from n. So the result of step 2 was x cubed minus x squared, so I take n, the numerator, minus that result. So be aware of the canceling signs here, and we get this. Now here's the maybe somewhat tricky part. Now we are going to replace n with this result. So n no longer refers to the numerator, n now refers to this guy. And then we compare the degree of this guy with the degree of the denominator. If the degree is smaller than the degree of the denominator, then we're done, and set the remainder to be whatever is currently occupying n. Otherwise, if the degree of this dude is still greater than or equal to the degree of d, repeat and do the step again, and do the procedure again. So in this case, n has degree 2, the denominator is degree 1. 2 is still larger than 1, so we have to iterate through the procedure again. Now, n has degree 1, the denominator has degree 1, so we need the degree of n to be strictly smaller than the degree of 1, so we have to iterate again. Okay, now we have a constant. The degree of a constant is 0. So 0 is in fact strictly smaller than the degree of the denominator, so that means we're done. So in every step here, notice we are adding a term to the quotient, and then the remainder is whatever we are left over with in n. So yeah, please take the time to review the steps here. It's simple. You know, every individual step is simple. You just have to make sure that you're following the algorithm closely. So what this achieves is that this polynomial division takes this dude and splits it into Q plus R over D. And now each of these individual pieces can be integrated somewhat simply. So hit these guys with the power rule, and then this guy can be attacked using this formula here. So in this case, A is equal to 1, and B is equal to -1. Yeah, so A is equal to 1, and B is equal to -1. And the whole thing is multiplied by 2, so that guy is just hanging out there. Of course, you could do this integration yourself by doing a U substitution, but if you just memorize these formulas, or at least have them on hand, I think that will speed things up tremendously, because the problems in this section tend to take quite a long time. They are rather involved, just in the amount of computations that you're asked to do. So this is our basic. This is our first strategy for breaking apart rational functions, is to do polynomial division. But polynomial division is only going to work if the degree of the numerator is greater than or equal to the degree of the denominator. So, what if the degree of the numerator is strictly smaller than the degree of the denominator, so that polynomial division cannot be done? In this case, we introduce our new strategy for this section, called partial fraction decomposition. So you're just going to have to sort of take me on faith with this, because I'm not going to be able to prove it, nor would proving it really be terribly enlightening. So for partial fractions, we're going to break this down into a number of cases. And the cases are going to depend on what the factorized form of the denominator looks like. So, case 1, suppose that the denominator can be written as a product of linear factors, where no factors are repeated. So a linear factor is just something of the form ax plus b. If that is the case, then we can decompose the rational function into a sum of terms like this, where each linear factor in the denominator is given a term in the decomposition, and the numerators are some unknown constants. So, as an example, suppose we were looking at this rational function here. The denominator can be written as 3 separate linear factors, linear because the highest power is just 1. And this would be decomposed into a single factor for each of these guys. So 1 factor for x, 1 for x plus 2, 1 for 3x minus 2. And the numerators are some constants, a, b, and c, which we have not yet determined. Okay? So this is the claim. The claim is that if the denominator is composed of linear factors, then there exist constants a, b, and c such that this decomposition is valid. The challenge, then, is figuring out what exactly these numbers a, b, and c are. So I think the best way to do this is to just jump in and do an example. Okay, so first off, we got this dude. So we're integrating a rational function. Now the first thing we should do is compare the degree of the top and the bottom to see if polynomial division is warranted. So here we have that the degree of the numerator is 2, right? That is the largest exponent of 2. And the degree of the denominator is 3. So polynomial division is only valid when the degree of the numerator is greater than or equal to the degree of the denominator. And in this case, that's not happening. The degree of the numerator is strictly smaller. So since 2 less than 3, we do not need to employ polynomial division. So we just jump straight into the partial fractions. So to do partial fractions, well, we need to factor the denominator. So let's see. Let's see what this ends up looking like when we factor it. So certainly we can factor an x out. So we're left over with 2x squared plus 3x minus 2. And then how do we factor this remaining guy? So this becomes 2x and x. We have a minus here, so we're going to have a plus and a minus. Although not necessarily in those spaces. Let's see. So what's going to work? I'm just sort of working it in my head. So if we do 1 and 2 like this, we get 2x squared plus 2. No, that's not going to do it. (2x squared plus 4 minus 1 minus 2). Okay, yeah, that'll do it. So use whatever method you want to factor things. I just sort of do trial and error in my head. If that takes too long, then of course we have other ways of doing it, but I don't really want to spend time on it. Since ultimately this course is about partial fractions and rather than algebra. Okay, so indeed we have a product of linear factors, and they are all distinct, right? These are all different. So our partial fraction decomposition will have the following form. So notice I'm not even dealing with the integral yet. The integral I can do once we have the decomposition figured out. So we're going to have one term for each factor, and the numerators are going to be constants. Like so. Okay, so now we need to figure out what those numbers a, b, and c are. Right? They are going to be some number such that this equation holds true. So what we're going to do here is I want to clear out the fractions. So actually, let me write this in its factored form. There we go. So I want to clear out the fractions so that I get just a single equation on one line. So to clear the fractions, multiply by the denominator, the original denominator, that is. So by this whole thing. Right? Because if we multiply both sides by this, then of course it'll cancel on the left-hand side. And we will be left over with, well, let's see. With this term, the a is going to cancel, but the 2x minus 1 and x plus 2 are still going to be there. Like so. For the second term, the 2x minus 1 is going to cancel, but the other terms won't. Then for the third one, the x plus 2 will cancel, but the other ones won't. So this is the equation that we have now. Okay, so for case 1, we have a pretty easy method of determining a, b, and c. So I just want to note that the following strategy only works for case 1. All right, so we are claiming that this equation is always true. We are claiming that there exist numbers a, b, and c such that this equation is true for any value of x. So what we can do is we can just pick a value of x arbitrarily, which simplifies this guy tremendously. So pick a value of x that cancels out one of the, or cancels out, nullifies, makes zero, one of the terms on the right-hand side. And what that's going to do is that's going to simplify the equation above tremendously. So for example, to make 2x minus 1 0, choose, or I should say plug in x equal to 1/2. Right? Solve that guy for x and we get 1/2. So if we plug in 1/2, what do we get? So 1/2 squared is 1/4, plus 2 times 1/2 is 1, minus 1, equals, well, now this dude just becomes 0, so that a disappears entirely, plus b times 1/2 times 1/2 plus 2, plus, and then this term also becomes 0, right? So I've literally done is I've just taken x equal to 1/2 and plugged it in. And that's great, because now the a doesn't appear, the c doesn't appear, so we just need to solve this equation for b now. And well, that's 1 down and 2 to go. So let's see, on the left, 1 minus 1, those cancel, so we just get 1/4. On the right, 1/2 plus 2 is, let's see, 1/2 plus 2 is 4 plus 1, so 5 over 2. 5 over 2 times 1/2 is 5 over 4, like so. So then to get b by itself, so these 4's in the denominator cancel, and then divide both sides by 5 to get b is equal to 1/5. Okay, so that's 1 constant down, 2 to go. So that's what we got when we made 2x minus 1 equal to 0. Next, let's make x plus 2 equal to 0. So that would be x equals negative 2. Okay, so negative 2 squared is 4. Minus 4 minus 1. So don't forget, 2 times negative 2 is negative 4. Equals. So x plus 2 is going to disappear, so that becomes 0. X plus 2 is going to disappear, so that becomes 0. And then for the last one, we have c times negative 2 times 2 times negative 2 is negative 4 minus 1. So let's see, 4 minus 4 minus 1 is minus 1. Minus 4 minus 1 is minus 5, times minus 2 is positive 10. Okay, and then to get c, just divide both sides by 10. Like so. All right, 2 down, 1 to go. So the only term which we have not yet canceled is x. So to make x 0, plug in x equals 0. So then on the left, we get 0 plus 0 minus 1. On the right, we get, so let's see, this term goes away, this term goes away, but we still have the first term. So a times negative 1 times 2. So let's see, negative 1 is equal to negative 2 times a. So a is equal to positive 1/2. Okay, so that is our partial fraction decomposition worked out, where a is 1/2, b is 1/5, c is negative 1/10. So now we can plug the partial fraction decomposition into the integral, and hopefully the things that we end up with are going to be much more easily integrated. So integral of this equals integral of all of this. Now, instead of a, we have 1/2. Instead of b, we have 1/5. And instead of c, we have negative 1/10. Okay, now all we need to do is anti-differentiate. So, this is 1/2 times 1 over x. So antiderivative of 1 over x is just natural log. This 1/5 is just hanging out, so you can pull that out of the integral. Integral of 1 over 2x minus 1. So let's see, that is one of these guys. Yeah, 2x minus 1. So a is 2, b is negative 1. So that's going to be this thing here. Like so. And then minus 1/10. Antiderivative of 1 over x plus 2. Well, same deal. Right, so the integration step here should be the easy one. And we can clean this up a little bit, just write this as 1/10 instead. Oh, yeah. Let me just put that there. And then yeah, may as well leave it at that. There's no need to really stress trying to get it to look simpler than that. Yep. Incidentally, when I write c here, I mean the constant of integration. I do not mean this thing. So maybe I should use a different letter. There, k. Because the word constant in German, I think, starts with the letter k. So, yeah. Okay, here's another one. So first off, we want to compare the degree of the numerator and the denominator. Well, the degree of the numerator is 0, and the degree of the denominator is 2. So no polynomial division needs to be done in this case. Right, the degree of a constant is 0, and basically just take this dx, move it to the side. We have 1 over x squared minus 4. And degree of d is equal to 2. So since 0 is in fact less than 2, we don't need to do polynomial division. Okay, so we need to move straight into partial fractions. So factor the denominator so that we can see what form our partial fractions are going to take. Well, this is easy enough. It's the difference of squares. So it just becomes that. And indeed, as is the case in case 1, we have distinct linear factors. So these guys are both linear, because the highest power is 1, and they are distinct. They are not the same. So the decomposition will have the following form. So 1 over x squared minus 4, which is the rational function that we're trying to break apart. So we're going to have one term for each factor. So a over x minus 2 plus b over x plus 2. So clear the fractions. And let me replace this with its factored form. So clear the fractions by multiplying both sides by the denominator to get 1 equals a. So the x minus 2 cancels, but we have the x plus 2 still. Here the x plus 2 cancels, but we have the x minus 2 still. Okay. Now, we're going to choose a value of x to get one of these dudes to cancel. So to get, say, x plus 2 equal to 0, plug in x equals -2. And then what happens? Well, the left-hand side is still 1. This guy becomes 0. This guy becomes b times -2 minus 2. So that's -4. So we get that b is equal to -1/4. All right, one more one to go. So the other factor is x minus 2. So to get x minus 2 to equal 0, plug in x equals +2. So we get 1 equals a times 2 plus 2, and then 2 minus 2 is 0 as desired. So 1 equals 4a. So a is equal to 1/4. Okay. So now let's plug the decomposition into the integral. Sure. So here's the decomposition, where a is 1/4 and b is -1/4. And it looks like, once again, we will be able to anti-differentiate both of these guys using this first formula here. So 1/4, we could just take that constant and pull it out. Natural log x minus 2 minus 1/4 natural log x plus 2. Plus some constant of integration. And there it is. Incidentally, with this case, we can simplify this a little bit further, because notice we can factor out this 1/4. So I don't know, just in case you see this in a multiple choice context, you can factor out the 1/4, and then we have log x minus 2 minus log x plus 2. And remember, a subtraction of logarithms is the same as a logarithm of a division. So we can push these two guys together to make a single division inside the logarithm. So x minus 2 over x plus 2, like so. So that would be an alternate way of expressing it. I mean, you could go even further. You could take this 1/4 and pull it inside and make it a power of 1/4. But whatever, we're just playing around at this point. I mean, in this example too, you could take this, pull it inside, take this, pull it inside, make it a power, take this, pull it inside, and then smash them all together using the laws of logarithms. But don't expend your energy. The partial fraction decomposition already takes enough time as it is. So that's not important. Okay, so that is case 1. That is the case where you factor the denominator and you get distinct linear terms. The next case that we could deal with is the case where you factor the denominator, but now some of the terms are not distinct. Some of the terms are repeated. In particular, you might get a power on one of the terms, right? Because repeated terms, you're multiplying them together. That means you're going to get an exponent. Now, in case 1, what we did is we gave one term in the decomposition to each factor, right? Each factor got one term in the decomposition. Now, if one of these guys had a power on it, then that's not exactly what's going to happen. So every time you see a linear factor that has a power, so for example, this is the linear factor x, but it has a power of 2. So you could say that it's being repeated, right? There's an x and then another x. Here we have a linear factor x minus 1 that is being repeated 3 times. So what you have to do is you have to have one term in the decomposition for each integer between 1 and the power. So here the exponent is 2. That means we have to have 2 terms for the x, one for each power. So one for x to the 1 and one for x to the 2. Here, since this linear factor has an exponent of 3, we need to have 3 terms for this, one for each power. So one for x minus 1 to the power 1, x minus 1 to the power 2, x minus 1 to the power 3. Okay? So the number of terms that each factor gets is the same as its exponent. So this guy gets 2 terms, this guy gets 3 terms. The numerators are still just constants, but yeah, we are now getting multiple factors per term, where the denominators step through all of the possible powers. So again, I'm not really going to explain why this happens. I mean, I don't really know myself. I've never worked through the proof that this works. Suffice to say that this is exactly what is needed just so that the algebra will all work out in the end. Okay, so let's do this integral here. So first off, compare the numerator and the denominator. Now here, we actually are going to have to start by doing a polynomial division because the numerator and the denominator have the same degree. And for partial fractions to work, we want the degree of the numerator to be strictly smaller than the degree of the denominator. So since the degree of the numerator equals 3 equals the degree of the denominator, in other words, the degree of the numerator is not strictly smaller, we need to employ we need to do polynomial long division first. Okay, so let's go through the steps. Let's work through the algorithm. All right. So step 1. So let me just make a note. So d is x cubed plus x squared. And whoops. N is initialized to be the numerator. But remember, through this algorithm, n is going to be changed at every step of the iteration. Okay. So step 1, take the leading term of n divided by the leading term of d. So that's x cubed over x cubed. That equals 1. And then the quotient, and then take whatever the result you got and add it onto the quotient. Okay, 2, take the result of step 1 and multiply it by the divisor. So 1 times x cubed plus x squared is, of course, just x cubed plus x squared again. Okay, 3, take the result of step 2 and subtract it from n. So n was all of this. Ugh. And subtract from it the result of step 2. To get, well, let's see, x cubed minus x cubed, that cancels. 4x squared minus x squared gives us 3x squared, and then everything else is left alone. And then this, the result of this computation, overwrites n. So now n has been overwritten with this value here. Okay, step 4, compare the degrees. So compare the degree of n, the new n, with the degree of d. So the degree of n is equal to 2, which is strictly smaller than the degree of d, which is 3. So if the degree of n is strictly smaller than the degree of d, then we're done. So set the remainder to be n, and then q is 1. So we are done now. So we get that this is equal to q plus r over d. Oops. Okay. So that's the first step. Now, with this second bit, the degree of the numerator is 2, the degree of the denominator is 3. So the degree of the numerator is strictly smaller than the degree of the denominator, which means that we are now in a position to do partial fractions. So start a partial fraction decomposition on this dude. Okay, so first off, we have to factor the denominator. That is easy enough, because I notice that I can pull out a factor of x squared, and we have x plus 1 left over. So the form of our partial fraction decomposition, so look back up to here. We've got linear factors, but one of them has a power. So we have the linear factors x and x plus 1, but this guy has a factor has an exponent of 2. So there's going to be 2 terms for this guy, 1 term for this guy. So let's see. And let's replace the denominator with its factored form. Let's see. So 2 factors for x squared, 1 for each power. So a over x, b over x squared. And then this guy doesn't have any power, so that only gets 1 factor. Like so. Okay. So let's clear the fractions. Like before. So over here, the x cancels. So we have x plus 1 left over. Over here, the x squared cancels, so we have x plus 1 left over. Over here, the x plus 1 cancels, but we still have an x squared. Okay. So here's the strategy. The strategy for case 1 was to pick values of x such that the terms on the right-hand side get canceled out. That's not exactly going to work this time. I mean, it'll work up to a point, but it's not going to work perfectly because, like, say for instance that you wanted to cancel out the x term here. Then you would let x equal 0. Okay, cool. So this goes away, and then you can solve for b. then let x equal -1. This goes away, now you can solve for c. But now, you don't have any more terms, you don't have any more things to cancel out. You have to solve for 3 separate variables, but there are only 2 distinct terms that you can cancel for. So, it's not perfect. It's not great. At the very least, the strategy doesn't lead you to the end point. It can get you partially there. Like you can solve for as many constants as there are distinct terms, but we want to do better than that. So for cases 2 and 3 below, our strategy to find the constants is to equate coefficients. So in other words, collect all of the x squared terms, the x terms, and the constant terms on the right, and then equate them with the corresponding terms on the left. So let me show you what I mean by this. So on the left, we have 3x squared plus x minus 1, so that's fine. And on the right, let's go ahead and distribute these guys. So ax squared plus ax. If we distribute the b, we get bx plus b. And then we still have that cx squared. Now let's collect all of the x squared terms together. So what are the x squared terms? Well, a and c. So a plus c times x squared, right? I just grouped these 2 terms together and then factored the x squared out of them. Or if you like, you could say that I'm combining like terms. Let's collect all the x terms together. So we have 2 of those, a and b. And then, well, we only have 1 term left over, so that's the constant term b. So now, on the left, the x squared term is 3. On the right, the x squared term is a plus c. So if we are claiming that these 2 polynomials are identical, like truly identical, then it must be the case that 3 is equal to a plus c. And same story with the other coefficients. So we obtain a system of equations, 1 equation for each term. So for the x squared terms, we get 3 is equal to a plus c. For the x terms, we get 1 is equal to a plus b. And then for the constant terms, we get -1. So let me just write like so. We get -1 is equal to b. Okay. So immediately, this tells us that b is equal to -1, so we got that. So now we need to solve the system. So b is equal to -1. We've already got that. Plug that into the second equation. So 1 is equal to a minus 1, right? Because b is equal to -1, so now I'm just plugging that in. So that means a is equal to 2. So if a is equal to 2, then that means 3 is equal to 2 plus c. So that means c is equal to 3 minus 2 is equal to 1. All right, so there we go. So there's our 3 coefficients, or there's our three constants. So now we can plug the decomposition into the integral. And then at the end of all of this, we're also going to have to deal with those upper and lower limits, but that's fine. So let's see. First, there was the output of the polynomial division. Next, this dude, then that dude got turned into the partial fractions. And now A is equal to 2, B is equal to -1, and C is equal to 1. So there we have it. There is this big, ugly rational function that has now been split into smaller, more manageable pieces. And by manageable, I mean you can find antiderivatives for them easily. So antiderivative of 1 is x. Whoops. Don't need the integral sign anymore. Antiderivative of 2 over x is 2 times the natural log. Minus. So with this guy, we're just going to have to hit it with the power rule. So x to the -2, that becomes negative x to the -1. So the minuses cancel. Like so. And then for this last one, this is just natural log of x plus 1. Again, going back to that formula at the beginning of the document. And then, so I almost forgot. So now we just have to finish this up by plugging in the bounds. But that should be easy. So we're going between 1 and 2. Between 1 and 2. So let's see. So if we plug in 2, we get 2 plus 2 log 2 plus 1/2 plus log 2 plus 1 is 3 minus, if we plug in 1, 1 plus 2 log 1 plus 1 plus log 2. So let's see. So log 1 is just 0, so that goes away. So 2 plus 1/2 is 2.5. Minus 1 is 1.5. Minus 1 is 1/2. 2 log 2 minus log 2 is 1 log 2. Log 3, and it's just by itself. Okay, so that's it. That's the end of it. Plug that into the calculator if you want. Doesn't really matter. All right, so I want to keep these videos from going over 50 minutes if I could at all help it. So continued in part 2, where I will deal with case 3. There is also a case 4 after this, but we're not going to worry about that because it's just really tedious and time-consuming. But we are going to go at least to case 3.